Hello everyone, my name is Takase. I am the Director of X-ray Imaging at Rigaku. In this presentation, I'm going to give you an overview of digital rock physics workflow, and I hope to show you that it is faster and easier than you might think. So this is how the workflow looks like. You run a CT scan on your rock sample and you have this gray level image CT scan. Then you can segment this image into the solid and the pore space. You can focus on the pore space and calculate things like porosity, for example, or you can focus on the solid part and calculate the grain size. For the pore space, you can also simulate percolation path or absolute permeability, and ultimately you can calculate or simulate things like a capillary pressure curve and relative permeability. And this is the entire workflow, and I'm going to walk you through starting from the experiment to get the CT scan and all the way to calculating the relative permeability. So we are looking at the digital rock physics workflow, but I should have mentioned that there are two approaches to get the insights or certain parameters for you to think about the development or production of oil and gas reservoirs. And one approach is the experimental approach, and the other one is the digital approach. And this is the one we're talking about in this presentation today. And those two approaches have pros and cons, and I'm not here to tell you which one is better or worse. And the other things, you're going to need them both anyway, depending on the situation. But I want to point out two important differences. The experimental approach tends to be slow. It could take years. But the digital approach is fast. This is in order of weeks. So if you're in a situation where you have to make a decision and you need to get some insights very fast and you don't have time to run experiments, then the digital approach might be a better choice. And you can run the experiments later for validation purposes. The other difference I want to point out is the sampling size. The experimental approach uses pretty large sampling size, but the digital approach is, in most cases, limited to a small sampling size to run the calculation faster. This is not a problem if your sample is pretty uniform, but if you have non-uniformity across the rock sample you're looking at, sampling size is something you need to be careful about for the digital approach. Now, you might be thinking that, well, don't we need really big machines and CT scanners and workstations to do this all? Well, not necessarily. Everything you're going to see in this presentation was a benchtop micro CT scanner. This one is called the CT Lab HX, and GeoDict software by Math2Market installed on a Dell Precision workstation. Nothing fancy. And by just using those tools, I was able to get everything I'm going to show you in this presentation. So let's start with the data collection. So this video is going to show you me putting a little plug sample, that's a sandstone, onto the stage of the CT Lab HX micro CT scanner and running a scan. This part is fast forwarded, but this was nonetheless only 2-minute scan. And once the scan is done, you got the CT image and you put it in GeoDict, and now you can do the segmentation to separate the solid and the air. There are different ways to do this segmentation, and we're gonna talk about it in a second. But once you run the segmentation, now you have this 3D digital rock you're going to use to run different analysis, calculations, and simulations. So you're ready to go at this point. So that's the data collection and a little bit of a segmentation. Now you have a CT scan of the sandstone plug, and it would look like this. The diameter was a little bit less than 10 millimeters. And if you look closer into this, you can see the individual grains in the pore space in between. Now, what we're going to do here is to put water and oil into that space and run a bunch of simulations. Get things like the porosity, the ratio between the open and the connected pores, absolute permeability, relative permeability. You can even estimate mechanical properties and also calculate forced imbibition characteristics. And they're all done by running simulations. Okay. When you do all those simulations, to get accurate results, the CT image quality matters. So now let's think about what kind of image properties we need to consider. When I say good image, what does that mean exactly? So number one, the size of this image or field of view matters. That needs to be large enough to represent the sample. If you look into this image, you will start to see those individual pixels or voxels eventually. In this case, this voxel is 5 micron in size, and that is called the voxel resolution. That's also important. And the third factor is the contrast and signal to noise ratio. So in this case, if you look at this cross section, you see high gray value that's the signal for the grains, and you have a little bit noise on top of it. And you want that signal to noise ratio to be high enough for you to do good segmentation. And that, by the way, is directly related to the scan time. So those are the 3 important parameters. Now, I'm going to give you a rule of thumb in terms of what those 3 parameters need to be. First, field of view. You want about 5 representative grains to fit in the field of view. And you can write this in an equation as REV, or representative elemental volume, being about the same as the effective grain size times 5. Now, in terms of how to determine the representative elemental volume and how to calculate the effective grain size, you can refer to those papers shown on the slide. But the rule of thumb is that your field of view needs to be the same or greater than 5 times of the typical grain size of your sample. Now let's take a look at the voxel resolution. So again, if you zoom into this image, you can see the individual grains in some pore throats. This pore throat is relatively wide, meaning that you have multiple voxels representing the throat. So this is good. This throat is pretty narrow, and you have only 1, maybe 2 voxels representing the pore throat, and that actually is not good enough. The rule of thumb for the resolution is that the voxel size with the voxel resolution needs to be smaller or better than 1/10 of the dominant throat size. So that's rule of thumb number 2. So next, I'm going to show you some examples of CT scans. This one is sandstone Idaho gray, which has relatively large grains. So we were able to use 5 micron voxel size 2-hour 20-minute scan, and this was good enough to do very accurate simulations. And you will see this sample a lot in this presentation. This is another sandstone liver rock, and this one has a smaller grain size, so we needed to use 2.5 micron voxel size, and we spent 17 hours to get the scan, and this was good enough to do good simulations. But what about shale? So shale tends to have a lot tighter structure. So in this case, we ran shale Eagle Ford sample using sub-micron CT scanner at 0.31 micron voxel size. It took 14 hours. And you can see some features. This is not a bad image by any means. However, to run digital rock simulations, this does not have enough resolution because you cannot see the pore space very well and you cannot resolve the pore throats. So this goes to show you that for most of the sandstones, you can use high resolution micro CT scans. But if you want to analyze shale, you might want to use SEM instead of CT. Okay. The next parameter is the signal to noise ratio. The rule here is kind of subjective, but shouldn't be too difficult one to judge. So this needs to be high enough to segment the image clean. This is a low signal to noise ratio scan, and this is a high signal to noise ratio scan. You run simple segmentation, you get results that look like those. This is not clean. You're not separating the grains and the pores cleanly. This one is clean. Thus, the signal to noise ratio is high enough for this image. So this is what you're looking for. To summarize, for the image quality, you want to pay attention to the field of view that needs to be big enough, and the voxel resolution that needs to be high enough, and the signal to noise ratio that needs to be high enough to have good quality CT images to run accurate simulations. Now let's move on to segmentation. So as we saw a second ago, this would be bad segmentation. And this is good segmentation because you don't have a lot of noise bits in either the pore space or the grain space. So how do we get this good segmentation? First of all, your data needs to be good. But even when the data is pretty good, you might have a hard time segmenting the image. So there are different ways to do image segmentation. You can simply use a thresholding to separate the image into two phases, or you can use machine learning, or you can even use deep learning. If you have a simple binary system, the thresholding might just work fine. But if you have a multi-phase system, you might need deep learning. Also, when the noise level is high, you might need machine learning or deep learning. Now, those techniques go from simple to complex. One thing to keep in mind is, as far as a simple method works, just stay with it. Only when the simple method doesn't work, try machine learning or deep learning, something more complex. And the reason is the more complex method takes longer to run the calculation. And also, they can make it a little bit difficult to keep your analysis traceable. Once you do the segmentation, you usually end up having just the solid or grains and air or the pore space. Now, if you want to do grain size distribution analysis, for example, you need to separate the individual grains. And that part is called object separation, and the results would look more like this. And once you do this, you can start running quantitative analysis. Now, once you do all of this, you can start routine core analysis. This segmented 3D model you can use for your digital rock analysis. If you look at the solid part, you can do the grain size analysis, and you don't want to look at those blue grains that are touching the interface of the field of view because those are not a full grain. So you remove them and just look at the grains that are fully included inside of the field of view. Then you can see the grain diameter, and they're all color-coded for their sizes. So that's the grain size. You can also focus on the pore space and calculate the overall porosity. You can also separate this into open pores and closed pores and get separate porosity for each. Now we can focus on the open pores, those are all connected, and use the GeoDict to simulate the percolation path in certain direction. So let's say we're going to do this in the Z direction. and tell the software to find a 10 percolation path. Then it will look at the open pore space and show you the percolation path. In this case, we are looking at 10 of them in the Z direction. You can also calculate the permeability tensor using this pore space. And once you do this calculation, you can visualize the velocity. I'm just showing an example in the Z direction. And you can also visualize the pressure mapping inside of the pore space. You can also simulate the mercury capillary pressure curve by virtually putting mercury into the pore space. So by doing this calculation, you can skip the experiment and get the mercury capillary pressure curve without running the experiment. However, when you do something like that, you wonder, well, how accurate is the simulation? And that's a fair question and a good question you should be asking. So I'm going to show you some comparisons between the two, experiment and the simulation. So this is a comparison of the experiment, the black line, and the simulation done by GeoDict, the red line, for mercury capillary pressure. As I understand it, GeoDict went through multiple generations of this simulation, and it got closer and closer and closer to the experiment, and now it's very close to the experiment, and you can use the simulation with confidence that your simulation is as close as you can see in this graph to the experiment. Another comparison I want to show you is this one. So this is not just, you can run the simulation for wetting phase or neutral phase or non-wetting phase and look at the actual experiment shown at the top and the simulation at the bottom and see that the simulation is simulating the actual event very, very well. This is a pretty complex calculation to run, but the GeoDict model is considering all the parameters you need to consider to run the accurate simulation, and it got to this point to be able to run simulations very accurately. Again, I'm not claiming that you can eliminate the experiment, but you can use the simulation with a certain confidence level when you have to get the results fast. Okay, now we looked at the routine core analysis results. Now let's take a look at the special core analysis. Okay, so by running the capillary pressure curve calculation, or the simulations I should say, you can gain the full capillary pressure curve plot. And by doing this, you will know the irreducible water saturation, and more importantly, you will have the residual oil saturation. I'm going to show you an example done using the same CT scan. So we use this Idaho Gray CT scan and run the simulation, and you can see that the spontaneous imbibition process is happening there. And at this point, it switches to a forced imbibition process. And at the end, you know what the residual oil saturation is. In this case, it was 0.149. And again, you can get those results without running. Now we have two phases, wetting phase and non-wetting phase. So you can also calculate the effective permeability versus wetting phase saturation. So this is a wetting phase and this is a non-wetting phase. And you can calculate the relative permeability based on this. And just as we did with the absolute permeability calculation, you can map the velocity or the pressure. So that's the entire workflow of digital rock physics, starting from running a CT scan and getting the full capillary pressure curve simulation. This entire process, as you saw in this presentation, was done just by using a benchtop CT scanner, a workstation computer, and GeoDict software, and you can do this all well within a day. This is not a weekly experiment. You can just get this done walking into the lab with a little plug in the morning, and you'll be walking away with the capillary pressure curve simulation by the end of the day. So I hope that this convinced you that this entire process might be faster and easier than you might think. Well, thank you very much for your attention. And if you want to learn more about X-ray CT, you can visit us at imaging.rigaku.com. And if you have any questions for me, you can connect with me on LinkedIn. Thank you very much.